Okay, in my last video, we were talking about the successive ionization energies, and I was giving you the example of magnesium, successive IEs. So recall, anytime you're looking at the first ionization energy, that means you're trying to remove that first electron from the neutral atom, that always is going to require the least amount of energy, irrespective of what the element is. Of course, other than perhaps argon, in which case that value by itself is going to be pretty high because it has a complete octet. But what I was trying to tell you was that if you have a relative trend, so for instance, for the case of sodium, perhaps the first ionization energy is going to be around, let's say it's 100 kilojoules. Now you don't have to memorize the numbers, you should just know what it means. Then the next ionization is going to be at least 10, if not 50 or 100 folds higher as compared to the first ionization. So that will be called as ionization energy 2. This will be called as ionization energy 1. I'm looking at sodium right now. So what that means is that the second ionization is going to be really difficult, and the reason why that is so is because you have achieved the complete octet, and the other point is that essentially you're trying to remove the electron from an already positively charged ion. So now you take a look at magnesium, where you need to go from magnesium to Mg plus and further from Mg plus to Mg2 plus, which will be the octet. And let's say you want to now ionize it one more time and give you something like an Mg3 plus, which is a hypothetical ion, of course. And if you wanted to do the comparison, of course, the IE1 is going to be the smallest, and when you look at the IE2 is going to be larger than the IE1 in this case, but probably not very large. Realize that even the IE1 in case of magnesium is going to be fairly large because you have a paired system. Magnesium has Z of 12, which means the electrons are 1s2, 2s2, 2p6, 3s2. 2p6, 3s2. So that means that in this case you have paired electrons, and they will need to be unpaired before they can be subjected to ionization. So the IE1 is going to be not very small. However, the relationship between IE1 and IE2 is that the second ionization is going to be ballpark in the same order. So let's say you had 100 kilojoules, perhaps the value for IE2 will be something like 175, close to about that. So it will not be very far away. But then you will see a tremendous difference between the first and second ionization, and when you compare that to the third ionization, and that is because now you have achieved the octet. So this will be something to the tune of like 10 times, 10 folds larger as compared to the other two numbers. Based on the ionization energy is what is called as the metallic character. So recall from class that as you go down in a group, the ionization energy that decreases because the effective nuclear charge on the valence electron is decreasing, and hence not as much energy is required, and the metallic character will increase. So the tendency to behave like a metal is going to increase. So the best metal that you will find will be cesium. Bottom left-hand corner is the best metal. And if metallic character increases as the size increases, then it's only normal to say that as the size decreases across in a period, as the size decreases, the metallic character also will decrease, which makes sense because on the right side of the periodic table, you have all your nonmetals. So really in an exam, you could be asked a question where you're either supposed to arrange several elements in the increasing or decreasing order of metallic characters. So just realize that down in a group, those are the metallic character is going to increase, whereas across in a period is going to decrease. If you try to go diagonally, so if you compare, let's say, lithium to magnesium, they are going to be about the same. So let's say I wanted to compare maybe phosphorus versus antimony for metallic character. Both of those belong to the same group, so all you got to see is antimony is further down in the group. That means the metallic character is going to be higher. The atomic radius is going to be higher as well, and the ionization energy is going to be lower. So IE is lower as you go down in a group, whereas atomic size and metallic character, they go hand in hand. They increase as you go down in a group. And the last property, of course, as you know, is the electron affinity. Electron affinity is the tendency of an element to attract electrons towards itself, and in this process, energy is released. So as you can perhaps envision that the nonmetals, they are going to have greater release of energy because they have a greater tendency to pull electrons towards themselves and accept them in their orbitals, in their valence shell, whereas metals are going to have pretty low numbers, even 0 for the case of the second group, and 0 for the case of group 8 as well, because group 8 is completely full, the second group is completely full as far as the S shell goes, and so they don't exhibit a tendency to accept any more electrons. So metals in general will have lower tendency to accept electrons. They always give electrons, so we usually refer to low ionization energy and high electron affinity in nonmetals and low ionization energy in metals. The combination of these two is going to give you the best ionic compound. So you can perhaps envision cesium fluoride, which has the biggest cation and the smallest anion. That's going to give you the strongest ionic bond. Now, I want to connect this chapter actually into chapter 10 and part of chapter 9 and part of chapter 10, unlike my earlier plan where I had thought that I would give you 9 and 10 separately. I just thought I would just put these together. So realize that while in an electronic configuration, let's say you're writing for oxygen and you know that Z of oxygen is 8, and so it's 1s2, 2s2, 2p4, and you know that the 1s2 will be the core electrons, and in order to find the valence electron you have to find the highest value of n and just add the number of electrons, the 2 plus 4, that will give you 6. Alternatively, you can also take a look at the location of oxygen on the periodic table, and since it is group 6, you would say that it contains 6 electrons in the valence shell. Now, Lewis theory simplifies things a little bit more. What Lewis theory suggests is that you can actually write down Lewis symbols for each of these elements. So for the case of oxygen, since you have 6 valence electrons, this will be one Lewis symbol where I am showing you 6 dots surrounding oxygen. Another way you could write this would be 6 dots in this manner, and it's immaterial. You can put perhaps 6 dots in this direction, leaving the, what would that be, like the left side, the west side, essentially devoid of any electrons. You can leave the east side without any electrons, north or south, however you want to put it, as long as it has 6 dots surrounding it, and following the principle that maximum that you can put on one side is 2, so that 4 directions, 4 times 2 is 8, and since you know you're trying to achieve a complete octet, these are going to be all possible octets for oxygen. On the contrary, think about oxide. In the case of oxide, it already had 6 of its own, and now you have given it 2 more. That means you have total of 8. That's how you're going to draw the Lewis symbol for oxide, and it has 2 negative charges. You know that because it has 2 extra electrons. If you had to show that the electronic configuration way, you would say that oxygen has Z of 8, and now you have added 2. That means you're trying to write down the configuration of neon. So it's going to be 1s2, 2s2, 2p6, the orbital diagram of which is going to be up and down for the 2s, the 2p singly filled, and then doubly filled as well. So it's all complete octet. Realize if you have to follow the ionic bonding according to the method of electronic configuration, you would say that, well, potassium, which has a configuration, let's say I'm trying to make KCl. Okay, you would say potassium, which has a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1 must get converted into K plus, in which case the 4s1 will be lost. So the configuration will become 1s2, 2s2, 2p6, 3s2, 3p6. So this is a complete configuration. The chlorine will become chloride. Cl will have to get converted into chloride. So likewise, you look for 17 for the case of Cl, 1s2, 2s2, 2p6, 2p6, 3s2, 3p5 is going to accept an electron, and so it will become 1s2, 2s2, 2p6, 3s2, 3p6, and that will be a complete octet. So essentially what you're saying is that the electronic configurations here are going to give you the K plus and Cl minus, which are going to coexist together, and the ionic compound is going to get generated. And if you consider this using the Lewis theory, it actually is pretty simple, because you know that potassium has 1 electron of its own. Cl has 7 electrons of its own. So what you do is you show the transfer of electron from potassium into the orbital for chlorine, so that it becomes K plus and Cl negative. So you can perhaps envision that writing the Lewis structure is a much more simpler method to show bonding. And this was the case of ionic bonding, writing the Lewis structure for ionic compounds. I'm going to take some time to go over some of the covalent compounds, so you really see the shared electrons, bonding electrons, non-bonding electrons, and how to go about it. Recall the case